In this video, we're going to talk about when two topological spaces are equivalent or homeomorphic. So our definition is that the topological spaces x tau and y tau prime are topologically equivalent or homeomorphic if there is a bijective function between them, mapping x to y, such that both f and f inverse are continuous. And if such a bijective function exists, that function is called a homeomorphism. So bijective means one-to-one and onto. It also implies that x and y have the same cardinality. Let's think about f and f inverse being continuous. So remember that continuity is related to open sets. So f continuous means for any v open in y, for any open set v in y, f inverse of v is open in x. So v open in y means f inverse of v is open in x. And because f inverse is continuous, that means for any open set u in x, f inverse, the inverse of f inverse of u, that's f of u, is open in y. So because f inverse is continuous, f of u is open in y. So that tells us that u is open in x, a set u is open in x if and only if f of u is open in y, if it's the case that f is a homeomorphism. We see that the first piece follows automatically from what we have above, this direction we see above, and the other direction, f of u open in y, implies f inverse of f of u is open in x, again because f is continuous, and this is equal to f inverse of f of u is just u open in x. So it's the case that if f is a homeomorphism, then for any open set u in x, or u is open in x if and only if f of u is open in y. Being homeomorphic is an equivalence relation. That means it's reflexive, symmetric, and transitive. We also already showed this in terms of metric spaces. Here, just thinking about it again, clearly reflexive does work because any topological space is going to be homeomorphic to itself through the identity function. That's going to be a continuous and bijective function from one topological space to itself. It's going to be symmetric because if we have a function f mapping x to y, then f inverse is defined already because f is bijective and both f and f inverse are continuous, so that's pretty immediate as well. Transitive, for transitive, showing that if x is homeomorphic to y and y is homeomorphic to z, then x is homeomorphic to z. To show that that is the case, we just need this theorem that if f mapping x to y and g mapping y to z are continuous maps between topological spaces, then their composition is also continuous. This we proved previously for metric spaces in the homework. And there were two different ways to prove this. You could have either proved it using the definition that relied on distance, or the equivalent definition of being a continuous function in a topological space, in a metric space, which relied only on open and closed sets. That proof also applies here because it's the same definition if we're using just open and closed sets and no distance. And the solutions to in the homework, I gave both proofs in the solutions. So we do have the proof that this is true for topological spaces as well, using just open sets, no distance. A property, so here is a new definition for us. A property P of a topological space is called a topological property or a topological invariant if whenever a topological space X tau has that property, any space that is topologically equivalent to it must also have that same property. So here's a couple theorems on that. First, separability is a topological property. The proof of this is in our book. Next, first and second countability are each topological properties. The proof that second countability is a topological property is going to be for homework, and the proof that first countability is a topological property we will prove right now. So we want to prove that first countability is a topological property. Let's just remind ourselves of the definition of first countable. So a topological space X tau is first countable if there's a countable local basis at each point in X. Beta sub X is a local basis at X if first beta sub X is a subcollection of tau, that is, each element of beta sub X is an open set, and condition 1, X is an element of each basis element, and 2, each open set containing X contains some basis element as a subset. So let's now do our proof that first countability is a topological property. So we're going to assume that X t tau and Y tau prime are homeomorphic topological spaces, and that X tau is first countable. So we want to show that Y tau prime is first countable as well. Since X tau and Y tau prime are homeomorphic, let's let F mapping X to Y be a homeomorphism, and let's let little y be an element of big Y. We want to show there is a countable local basis at Y. And if we do that, we will have shown that Y tau is first countable. Since F is a homeomorphism, that means that F is onto or surjective. And so there exists some X in the big set X such that F of X is equal to our point Y. And then since X is first countable, that means that there is a countable local basis at X. Let's call it the collection of sets BI, and I can use I as a subscript because this is some countable set. It might be finite or it might be a countably infinite set. Now, what do we need to show? First of all, we need to show that, what do we want to show? We want to show that the collection F of BI is a basis at Y. So first of all, is each of the sets F of BI open? Yes. Since BI is a countable base or is a basis, that means BI is a subcollection of tau, and therefore each BI is open. And since F is a homeomorphism, that tells us that F of BI is open for all I, which tells us that the collection F of BI is a subset of tau prime. Okay, so that's one piece down. Our first condition, once we know that those elements truly are open sets, to show that the collection F of BI is a local basis, we want to show that Y is an element of each of them. So since X is an element of BI for all I, that tells us that F of X is an element of F of BI for all I. And so yes, y, which is equal to f of x, is an element of each of those sets. 2, we need to let V be an open set in Y, an open subset of Y, containing the point little y. And we want to show then that there's some element of this thing that we hope is a basis. There's some f of bi such that f of bi is contained inside of V. We need to show that. So then f inverse of V is open since f is continuous because f is a homeomorphism. And so there is some bi in this collection of basis elements. Maybe let's call it b sub k instead of b sub I. There's some b sub k in this countable local basis such that x is in b sub k, which is a subset of f inverse of V. Now this tells us that then f of x, which is equal to y, is an element of f of bk, and that is a subset of f inverse of V, which is in fact V. And so we have shown the second condition for being a local basis at y. So therefore, the collection f of b sub I is a local basis at y, and since the collection b sub I is countable, that means that the collection f of b sub I is 2. So we have a countable local basis at y for any y in the topological space. Therefore, y is first countable, and so we've shown that if x is first countable and y is homeomorphic to it, then y is first countable as well. Therefore, first countability is a topological property. Here's a definition that we've alluded to. So a topological space X is metrizable if the topology of X can be generated by some metric. So, for example, any set X with the discrete topology is a metrizable topological space. Remember that the discrete metric is the topology tau sub d, where every subset of X is open. This is given by the discrete metric, where the distance between 2 points is 1 if x is not equal to y, 0 if x is equal to y, and therefore the ball centered at x of radius 1/2, or any distance less than 1, is going to be equal to the singleton set just x. That's an open set, and so therefore A equals the union of x in A. The union of these singleton sets is therefore open because arbitrary collections of open sets are open. And so, yes, it is the case that every subset is open in that metric space, and therefore the discrete topology is given by a metric and is metrizable. As another example, the real numbers with the usual topology. So this is given by, so this is where the open sets are the open intervals in R. This is given by the usual metric in the real numbers, that the distance between x and y is the absolute value of x minus y. So here's a theorem that we're not going to prove for now, but we're going to state and assume is the case, that the property of being metrizable is a topological property. So if two topological spaces are homeomorphic and one is metrizable, the other one is too. If one is not, then the other one also must not be. Here's an example of something that is not a topological property. So being a bounded set, X being bounded, is not a topological property. As an example, we saw that the set of all real numbers with the usual metric and the open interval, the set of all real numbers, negative infinity to infinity, and the just open interval from 0 to 1 with usual metrics, and therefore with usual topologies, open intervals are open, are homeomorphic. We saw that this was the case for them as metric spaces, and so therefore it's also true for topological spaces. In fact, we saw that any open interval AB is homeomorphic to any other open interval AB. But because these are both homeomorphic, and it's clear that this is unbounded and this set is bounded, that means that being a bounded set is not a topological property. So two topological spaces can be homeomorphic to one another, but one is a bounded set and the other is not. So in general, to show that two topological spaces are homeomorphic, we need to find a homeomorphism between them. We need to, in other words, find some bijection, F mapping one space to another, such that F and F inverse are continuous. So we just need to find such a homeomorphism. To show that two spaces are not homeomorphic, there's two sort of ways we could do that. One is we could prove that it is not possible to have a homeomorphism between them. This can often be tough. So this is not just showing that a particular function is not a homeomorphism, but that no such homeomorphism can exist. In some cases it might be obvious, like if the cardinality of x is not equal to the cardinality of y, then that's immediate because there's no bijection between them, and therefore no homeomorphism between them. But if they do have the same cardinality, then it could be kind of difficult. Another option is to show that they don't share some topological property. So if two topological spaces don't share a topological property, that means they cannot be homeomorphic to one another. As an example, if we think about the real numbers with the finite complement topology and the real numbers with the half open interval topology, that's the one generated by half open intervals, then these cannot be homeomorphic. These are not homeomorphic. And how do we know? Well, we've proven a couple of properties about each of these. So we showed that this is not first countable in our notes when we were looking at first countability. We proved that the finite complement topology, that the real numbers with the finite complement topology is not first countable. And we proved in the homework, so this we proved in the notes, and in the homework, the last homework, we proved that this is first countable. So because these do not share a topological property, that means that these two topological spaces are not homeomorphic to one another.